All right, if you're building on Ethereum, you know the terrain. Today, we're digging into something pretty big, a change that's really reshaping the foundation, the EVM Object Format, EOF.
Yeah, EOF. It's a significant shift. Think about the current EVM.
Right.
It's like this huge open digital space, right?
Right.
You can throw pretty much any bytecode at it and it just chugs along, trying to execute byte by byte. Patel Billick had a great phrase for it, a garbage eating machine.
Yeah, that captures it pretty well. Just consumes whatever's there.
But EOF, that's like taking that chaotic workshop and seriously organizing it.
Yeah.
You've got labeled sections for tools, the opcodes, clear blueprints, the code sections, defined functions, your materials, the data, all neatly stacked and separate.
Structure, that's the key word.
Exactly. Structure for the EVM.
So our mission today in this deep dive is really for you, the developer listening. We want to unpack how EOF, this fundamental change, is going to affect how you actually build smart contracts.
We're aiming for contracts that are more efficient, definitely more secure, and more future-proof.
And it's not a small tweak, is it? People are calling this maybe the biggest EVM change since Ethereum, well, since Genesis.
It's certainly up there. It's a major architectural evolution. Now, when we say EOF, it's not like one single proposal. It's actually a bundle.
Okay.
Around 11 EIPs, Ethereum improvement proposals, all working together. And crucially, most of them depend on each other. They're designed as a package deal.
Got it. So a coordinated effort. But at its heart, technically speaking, what's the core change EOF brings? What's happening under the hood?
The absolute core is EIP 3540. This introduces a versioned container format for EVM bytecode.
A container, so instead of just raw bytes.
Exactly. Instead of that raw stream, your compiled contract code gets packaged into this defined structure. The big idea is separation. You have dedicated sections for your executable code, another for static data, and potentially separate sections for distinct functions.
That sounds fundamentally different from now, where code and data are kind of mixed together in one long sequence.
It is. It's a major departure.
So could you walk us through this container? What does an EOF contract actually look like? Its anatomy.
Sure. So every EOF contract starts with a header. Think of it like the file header or metadata. It kicks off with these specific magic bytes, 0 by EF100, 0.
Okay, like a signature saying, hey, I'm EOF.
Precisely. Then comes a version number, currently version 0 by 01. After that, the header lays out the structure. It specifies the type section info, the number of code sections and their sizes if there are any optional subcontainers, the size of the data section.
So like a table of contents for the contract itself.
That's a great way to put it. And it ends with a terminator byte, 0x000, just to clearly mark the end of the header.
All right, header gives the map. What about the body, the actual content?
Right after the header comes the body. It starts with a type section. This defines the characteristics for each code section. Things like the number of inputs it expects, the number of outputs it returns, and critically, the maximum stack height it will need during execution.
Stack height prediction. Interesting.
Yeah, we'll come back to that. Then you have the code sections themselves, one or more. This is where your actual EVM bytecode lives, but now organized into these logical units.
Okay.
You might also have optional container sections, maybe for deploying other contracts. And finally, the data section. This holds any static data your contract needs, kept completely separate from the executable code.
So the real takeaway is that clear separation. Code is code, data is data. Unlike the legacy EVM where it's all interwoven.
Exactly. And this structure isn't just for neatness. It unlocks some really tangible advantages for developers.
Okay, let's get into those advantages. What's the first big one?
I'd say a huge one, especially for security and reliability, is code validation at deploy time. That's EIP 3670.
Deploy time validation. That sounds significant. How does that work?
Well, EOF enforces a whole battery of checks before your contract code is even accepted onto the blockchain.
Before it goes live.
Yes. If your contract bytecode contains any invalid EVM instructions, maybe an opcode that doesn't exist, or a PUI-SH instruction with incomplete data gets caught, or, importantly, if it tries to use instructions that are deprecated within EOF contracts, like call code, or the big one, self-destruct.
What happens then?
The deployment just fails. The transaction reverts. The contract is rejected, flat out.
Wow. That's a big shift from the current model where most validation happens during runtime, right? When the code actually executes.
Exactly. Right now, a contract with, say, an invalid jump destination might deploy successfully, but then fail or behave unpredictably only when that specific code path is hit later on. That could be minutes, days, or even years later.
Potentially causing real problems on a live contract.
For sure. Unexpected failures, wasted gas, maybe even security vulnerabilities if the failure state is exploitable. By catching these structural and instruction-level errors before deployment, EOF acts like a much stricter gatekeeper. It prevents flawed or potentially dangerous code from ever hitting the chain state.
That's a major security enhancement. Catching bugs before they even get deployed.
Definitely. Early detection is key.
Okay, that's a compelling benefit. What's another advantage this structure enables?
Another really critical one is how EOF handles control flow, moving away from dynamic jumps. EIP 4200 introduces static relative jumps.
Okay, so the current JMP and JJO-MPI opcodes, they take their destination address from the stack, right? Which can be calculated at runtime.
Correct. And that dynamic nature makes it quite hard sometimes for tools, and even humans, to figure out all possible execution paths just by looking at the bytecode.
Yeah, analyzing code with dynamic jumps can be a headache.
EOF replaces them with RJJOMP, RJJOMPI, and RJJOMPB. The R stands for relative. Instead of an absolute address, these instructions use an immediate offset value, a signed integer encoded right after the opcode itself.
An offset, so it says jump forward X bytes or jump back Y bytes?
Exactly. The jump target is fixed relative to the current instruction and known at deploy time. This seems subtle, but it's huge.
How so?
Because the control flow graph is now static and easily determined up front. Compilers love this. Static analysis tools can map out execution paths much more reliably. And the EVM itself doesn't need to do runtime jump-est analysis for these jumps, which might offer some slight performance improvements.
So, clearer analysis, potentially faster execution. It sounds like moving from vague directions to precise GPS coordinates baked into the code.
That's a good analogy. It removes ambiguity.
Okay, makes sense. What about organizing the logic within a contract? Managing large contracts, keeping things clean, that's always a challenge.
Absolutely, and that's where EIP 4750 comes in, introducing the idea of functions as actual separate code sections.
So multiple code sections within one EOF container.
Yes. Instead of one giant blob of bytecode where you use jumps to simulate function calls, EOF lets you define distinct, independent code sections. Each one could effectively act like a self-contained function or subroutine.
That sounds much more modular. How do you call these sections?
EOF introduces new opcodes specifically for this. CALLF to call a function, another code section within the same contract, and RETF to return from it.
CALF and RETF. Okay.
This makes organizing complex logic so much cleaner. Think about readability, maintainability, code reuse within the contract. It moves away from those potentially complex jump patterns we use now.
That feels like a big step up for developer experience. I also heard whispers this might tie into account abstraction.
That's right. The ability to define these multiple callable code sections, essentially multiple entry points within a single contract wrapper, aligns really well with some AA concepts, like having different validation or execution logic accessible through the same account address. It offers more flexibility.
Very interesting. Okay, let's switch gears slightly. The EVM stack, always something developers have to wrestle with. How does EOF help there?
EIP 5450 tackles this with deploy time stack validation.
More deploy time checks.
Yes. Remember how the type section in the header defines the maximum stack height for each code section? EOF uses that information, plus analyzes the opcodes within each section to mathematically prove at deploy time that the code, when executed, will never cause a stack underflow or overflow within that section.
Wow, it can guarantee no stack errors before runtime.
For valid EOF code, yes. It verifies the stack consistency for every possible path within a code section. This is powerful because it means the EVM might not need to perform certain stack checks during actual execution, which could lead to performance gains.
Fewer runtime checks, potentially faster execution. Makes sense.
And related to this, although not strictly part of EOF itself, but often discussed alongside it, are some new stack manipulation opcodes.
Oh.
Yeah, opcodes like DPN, SwapEN, and Exchange. These let you duplicate or swap stack items much deeper down than the current DUP116 and SWAP116 allow. Think potentially accessing up to 256 stat slots, like local variables.
Wait, up to 256? That would basically kill the stap too deep error in Solidity, wouldn't it?
It certainly aims to address that major pain point, yeah. It gives compilers much more room to manage variables effectively without hitting that limit.
Those sound incredibly useful.
Okay, what other core EVM parts does EOFS touch?
Gas observability and calls get a revamp with EIP 7069. This changes how instructions like call, static call, delegate call handle gas.
How so?
Currently, the caller can specify exactly how much gas to forward with the call. EOF changes this. The original opcodes are slightly modified, and new variants are introduced, like XL, ecstatic call, xdelegate call.
X variants.
Yeah, and the key difference is these new variants automatically forward the maximum available gas possible within the current calling context. You don't specify an amount, it just sends basically all remaining gas minus safety buffer.
Huh. Why remove the ability to specify the gas?
The main driver is future-proofing. Gas costs for opcodes change over time with network upgrades. If a contract relies on sending a very specific amount of gas, a future gas schedule change could unexpectedly break its internal logic if that amount is no longer sufficient.
Ah, so it makes contracts less brittle to future gas repricings. Exactly. It improves forward compatibility. It also helps simplify reasoning about gas usage and contributes to safety measures needed for things like address space expansion in the future. Oh, and EIP 7069 also adds return data load, a more efficient way to read specific chunks of return data from calls.
Got it. More robust calls. And finally, what about creating new contracts? Does EOF change deployment itself?
It does. EIP 7620 introduces new opcodes tailored for creating EOF contracts, create, createx, and return contract.
New creation opcodes.
Yep. They're designed to work with the EOF structure, including this interesting concept of subcontainers, allowing EOF contract to embed the init code for other contracts it might deploy. Also, a key change is that the existing create2 opcode will be modified to fail if someone tries to use it to deploy bytecode that starts with the EOF magic bytes, 0 by EF.
So forcing EOF deployments through the new EOF-aware opcodes. Essentially, yes. Ensuring that things declared as EOF are actually created correctly. And there's a potential efficiency gain here, too. These new opcodes might avoid the need to copy the contract's init code into memory during deployment, saving gas.
Okay, wow, that's a lot. Execution, control flow, stack, gas, calls, deployment. EOF really touches almost every core aspect of the EVM.
It's comprehensive.
So, stepping back, what are the big picture impacts for the ecosystem and especially for developers listening right now?
Well, for developers, the promise is a significantly better experience. We touched on eliminating stack too deep. That's huge. The clear structure should make debugging easier. Some argue debugging could be miles ahead because removing things like gas introspection and having static control flow means the execution trace of optimized versus unoptimized code might become semantically identical, simplifying analysis.
That debuggability point alone sounds like a massive quality of life improvement.
It really could be. And beyond the direct coding experience, think about tooling.
Right, you mentioned static analysis. Yeah. The structured format, the clear separation of code and data, static jumps. It's all a massive boon for static analysis tools, formal verification platforms, decompilers, debuggers. They can understand the code much more deeply and accurately. This should lead to better bug finding, more reliable security audits.
And L2s.
L2s could benefit too, potentially. Easier analysis might help with things like fraud proofs or ZK EVM implementations, though the specifics depend on the L2 architecture. We're already seeing tools like Foundry actively building out EOF support for decoding and working with this new format.
Makes sense. And security. We touched on validation, but anything else?
The deploy time validation is the big one, preventing faulty code. Static jumps remove a class of bugs and potential exploits related to dynamic jump destination manipulation. And critically, banning self-destruct within EOF contracts means the code you deploy stays deployed and analyzable. No disappearing logic.
That seems vital for transparency and security. Okay, what about gas? Is EOF going to make my contracts cheaper to run?
That's not the primary goal, like slashing specific opcode costs. But yes, there's potential for overall gas savings, mostly indirectly. Removing the need for certain runtime checks, like some stack validation, could save gas. The potential for compilers to generate more optimized code due to the clearer structure and new opcodes might also lead to savings. Early estimates floated around are maybe in the 3–5% range for overall efficiency gains.
Okay, so not dramatic savings, but noticeable.
Potentially. And another related point, EOF comes with a proposed increase to the maximum contract size limit.
Oh, bigger contracts.
Yeah, the proposal is to raise it from the current 24 kilobytes for legacy contracts to potentially 64 kilobytes for EOF contracts.
Wow, that's a significant jump. Allows for more complex applications.
It does. But the hope is that the modular function structure, called FLORETF, encourages developers to use that extra space wisely, building larger applications from well-defined, reusable components rather than just one giant monolithic contract.
Right, encourages better design patterns, even with more space. Okay, the million-dollar question for many listeners. What happens to all the existing smart contracts out there? Do they need to be rewritten? Will they break when EOF activates?
Oh, absolutely not. This is crucial. EOF is not retroactive.
Okay, phew.
All existing contracts deployed before the EOF upgrade goes live will continue to run on the legacy EVM rules. They won't be affected. EOF rules only apply to new contracts deployed after the upgrade.
So old contracts are safe, but new deployments must use EOS.
Once the upgrade is live, yes, the intention is that new contract deployments would likely need to conform to EOS standards to be valid. We'll need to see the final specification for the transition details.
And what about things like proxies? Can I upgrade my existing system to use an EOF implementation?
Yes, that's a key migration path. If you have an upgradable proxy contract now, you could deploy a new implementation contract written using EOF and then point your proxy to that new address. Your users interact with the proxy as always, but the logic executes under the new EOF rules.
So migration is possible through standard upgrade patterns. What should developers start doing now?
I'd say start thinking in terms of modularity even more. Use libraries, break down complex contracts, familiarize yourself with the EIPs, they're quite readable, and keep an eye on your development tools, Hardhat, Foundry, etc., as they roll out EOF support for compilation and testing.
Good advice. Get ahead of the curve. Now, this is a huge change. Are there any sticking points, concerns, or ongoing debates around EOF?
Oh, definitely. It's a complex upgrade touching the very core of Ethereum. There have been debates, about whether such a big L1 change is the right priority versus focusing purely on L2 scaling.
The L1 versus L2 focus debate.
Exactly. And EOF was actually planned for earlier upgrades but got postponed, which highlights the technical challenges and the need for extensive testing. Implementing and maintaining two versions of the EVM legacy and EOF in client software also adds complexity for the client teams.
So it's not without its challenges and discussions.
No major upgrade ever is. But the core developer community seems largely aligned that the long-term benefits, security, developer experience, future-proofing, make it a necessary and worthwhile evolution for the EVM.
Right. It sounds like the consensus is that the growing pains are worth the long-term gain. So let's try and summarize. If you're an Ethereum developer listening, what are the absolute key takeaways about EOF you should walk away with?
Okay, key takeaways. 1, EOF brings structure and validation to EVM bytecode via a container format. 2, major benefits are deploy time validation for enhanced security, static relative jumps for clearer control flow and analysis, and proper functions, called FRETF, for modularity. 3, stack validation at deploy time, potentially removing runtime checks and helping eliminate stack too deep issues, especially with new opcodes like DUP and SYPM. 4, changes to calls, XL, make contracts more robust against gas repricing.
And 5.
5, better tooling support becomes possible, improving static analysis, debugging, and formal verification. And importantly, existing contracts are unaffected. EOF applies to new deployments post-upgrade.
So enhanced security, better efficiency potential, improved tooling, a more structured way to build. It sounds like a significant upgrade for developers.
It really is. While migrating existing stuff is optional, all new development on Ethereum L1 will eventually leverage these advantages. It's setting a new baseline.
It's laying the groundwork for the next generation of dApps, really.
Precisely. It's a foundational upgrade.
This has been incredibly illuminating, a fantastic deep dive into the EVM object format. It's clear this is something developers absolutely need to get familiar with.
Agreed. And maybe a final thought to leave people with.
Hmm.
Given these really fundamental changes to how the EVM works, how code is structured and validated, how do you, the developer, think this will change your workflow? How might it change the architecture of the decentralized applications you design and build? What new possibilities does a more structured, more predictable, more verifiable EVM actually unlock? It's worth pondering. We definitely encourage everyone to check out the EIPs linked in the description and follow the community discussions as EOF gets closer to deployment.